Okay, so here is the rest of it, or well, not rest of it, but most of the rest of it. So here's where we're going to start. Now, in the last one, we said, look, we have two vectors, right? We have vector B, okay, and we chose vector B to be a minimal vector basis, a minimal basis, or excuse me, a basis with minimal members, right? So n, and we said, okay, let's take any other basis D with members of its delta, and what we want to do is we want to show that D has no more than n members in it. So that's pretty much where we were left off. Now, at this point, we want to also mention that, okay, the basis B spans the space, right? We know that by definition of a basis. And delta 1, which is in D, so we took delta 1, is in the space. So what does that mean? It means that D, the vector D1, delta 1 rather, not D, delta 1, is a non-trivial linear combination of the elements of B. Okay? Now, by the exchange lemma, we can swap delta 1 for a vector in B. And that will result in a new basis, basis 1, or B1, where one element is going to be delta 1, and all the other n minus 1 vectors are going to be betas. Okay, so now we've got one delta vector in this new basis, and we've got one less beta in there. Okay? Now, this forms the base step of an argument for induction. So this is going to be an inductive argument. So now, what we're going to do is the inductive argument is going to start with assuming that there exists a b sub k, right, for some k that's at least 1 but less than n. That contains k members, right, using this reiteration, k members of D and n minus k members of B. Okay, so we're assuming that this process up here is going to hold for b sub 1 through b sub k. Now, we know D has at least n members in it, right? Because B is minimal, so the basis D has to have at least n. Okay, could have more, but it has at least n. Okay, right, and we're trying to show that it doesn't have more, but that's what we're trying to prove, right? Now, D has at least n members, so there has to be another delta vector, k plus 1. And so we want to represent it as a linear combination of the elements of b sub k. Okay, now, this this brings us to a key point. Now, in that representation, at least one of the non-zero scalars must be associated with a beta sub I, or else that representation would be non-trivial, would be a non-trivial linear relationship among the elements of D, but remember, D is linearly independent, right? Because it's a basis. Okay? So, we're going to exchange delta k sub 1 right? So we're going to do the same thing. We're going to say delta k sub 1, we're going to exchange for the betas, what are the betas in B. And now we're going to get a new basis, which is going to be, right? Which is going to be B sub k plus 1, right? And so it's going to have one more delta vector and one less beta vector than the previous basis B sub k. Now, here's the thing. We can repeat this over and over again until all of the betas in B have been swapped with a delta in D. We could do that. Now, if we do that, and so that B sub n contains delta 1 through delta n, right, because we've done it n times. Now, here's the thing. Once we do that, D cannot have more than these n vectors, because any delta vector n plus 1 that remains would be in the span of B sub n, since remember, B sub n is a basis, and hence would be a linear combination of the other deltas, which would contradict the fact that we're assuming D is linearly independent. And therefore, D cannot have more than n members. And we're done.